Hello everybody, in this video we will have a gentle introduction to matrix algebra, matrices. So the concept is related to solving a system of equations, and I believe you guys have been solving system of equations since probably middle school, I guess. Right, so let me just go ahead and give you an example of a system of equations with two equations and two unknowns. So usually system of equation problems. Okay, so let's first write out the example. Would have equations like this: 2x plus 3y equals say 29, and x minus y is simply equal to 2. So this is a system of linear equations, to be more specific. Both equations are in linear form. So when I say system of equations, let me clarify here. System of linear equations. The whole thing will be related to what we call as matrix algebra, or also known as linear algebra. Linear is a word which has been derived from the word line. All right, so how do you solve this system of equations? Well, the method that we learned since probably, like I said, middle school, is one method would be substitution. So we can just, using the second equation, we can turn the second equation as x equals 2 plus y, and now we can go ahead and substitute this expression into the first equation. So therefore we would get, so anywhere we see x in the first equation, replace it with 2 plus y. So the first one there, 3 times y is equal to 29. Now we can go ahead and solve this for y. First, let's distribute here. 4 plus 2y plus 3y is equal to 29, further implying that we can move the 4 to the right hand side, so we would end up with 5y equals 25, and now dividing both sides of this by 5, that gives us y equals 25 over 5, which is just 5. And from here we can substitute this value into our expression again. That would imply that x is simply equal to 2 plus 5. That's just a 7. That's it. So we were able to solve this system of equations where we had this system of two linear equations, I should say. All right, so both equations are clearly linear. So now we would like to introduce a new concept, the concept of matrices, which is the backbone of the building blocks of linear algebra. And the idea is extremely simple. So what we will do is we will separate the coefficients in the system of linear equations from the variables. So it happens like this. So let me just go ahead and use a different color. So because there is 4 coefficients effectively here, 2, 3, an invisible 1, and then another invisible -1. So that would be my matrix of coefficients multiplied by a vector of variables, and that would be equal to, on the right hand side we have 29 and 2. All right, so this is the same system of equation in matrix form. All right, so this is matrix form. Let me just explain a little bit what does that mean and how to interpret this. The interpretation is actually very cool, and it goes along the following way. So that first row of numbers, we will multiply them component wise with this column matrix, this column vector, or if you want. So the way it will work is the following. Let me use this color. So 2 times x is 2x, and there you go, we have the same expression over here, plus 3 times y. Do you guys see that? 3y over here, and that better be equal to the first one, 29. Then what we will do next is to take that second row and multiply with the variables one more time. 1 times x that time, let me use gray color, 1 times x plus minus 1 times y, which is just 1 times x is x, minus 1 times y is minus y, x minus y is equal to 2, and indeed that was the second equation. That's it. So once you convert the system of equations into this matrix form, if you want, I can do the following simplification. Therefore, so this matrix 2 by 2 matrix, we can represent it with the letter A, capital A. That's a standard form to represent matrices. That one, this vector of variables, I can just represent it with the letter V. So A times V is equal to, on the right hand side, we have another vector which I can represent it as B if you want. So if you want to find the value of V, that vector with V whose components are x and y, all you need is to multiply both sides of this matrix operations by the inverse of A, on the left hand side, to be honest. Alright, so what it does is the following. Let me use a different color so you guys have a clear idea. I'm going to multiply the left hand side of the, the left hand side of the equation, this matrix equation, with the inverse of that matrix A, whatever that means, and we will do the same thing on the right hand side as well. That's it. So once I do that multiplication, these two will just give me an identity. An identity multiplied with V. On the right hand side, we still have my A to the minus 1 times B. Identity multiplied with the any vector is still V itself, and there you go. So it is just A to the power minus 1 times B. So the inverse of matrix A times B. So therefore all that remains is to first identify the inverse of matrix A and then multiply it with that vector B here on the right hand side. So what we need is, let's start with finding the inverse of this 2 by 2 matrix, 2, 3, 1, minus 1. So how do we find the inverse of this matrix? There's this really cool idea called Gaussian elimination. Gaussian elimination. And it goes along the following way. And we can discuss the relevance of this approach, which is a really cool approach. So we will do some what we call as row reduction operations. And the good news is, by the way, Excel can do this pretty easily again. So for the time being, let me just show you manually how to do it. But at the end of the day, you guys will most likely do most of this stuff in Excel. All right, so how do we do that? So it's this cool idea. Let me just move this a little bit. So we want to find the inverse of 2, 3, 1, minus 1. So what I do is I construct an augmented matrix, 2, 3, 1, minus 1. And next to it, I write this other 2 by 2 matrix, 1, 0, 0, 1. We call that matrix the identity matrix. Let me actually move everything all the way to the right. There you go. So in a sense, I just constructed this imaginary 2 by 2 matrix on the right. So what I will do is row reduction operations to this, right now 2 rows and 4 columns, 2 by 4 new augmented matrix, in such a way that ultimately, after I'm done, it will take me multiple steps. At the end of all these steps, at the end of all these steps, what I want is to have this 2 by 4 matrix, but this time on the left hand side, I want 1, 0, 0, 1, and whatever are these entries over here will turn out to be the inverse of that matrix 2, 3, 1, minus 1. Just to clarify, the inverse of an n by n matrix will end up being an m by n matrix again, and only square matrices will have inverses. Square matrix is a matrix whose number of rows and columns are equal, basically. All right, so let's do it. So how do you do that? So the Gaussian elimination works in the following way. So you have basically three operations that you are allowed to do. So the operations that you are allowed to do is swapping, swap, multiplying any row with, so when I say swap, swap rows, multiply any row by a scalar, by a number, basically. And the third one is you can multiply a row with a scalar and then add it to another row. Add row to another, add row to another one, to another row. That's it. So these are row operations. All right, so these are row operations, and let's go ahead and implement those operations. So here I start. So well, let's just create this if you want. Let me just make sure everybody's on the same page. So what I want is, because ultimately that's what I want, first order of business will be to totally well, let's start by making that leading entry 1. So how can I make that leading entry 1 here? By just simply multiplying the first row by 1/2. Am I allowed to do that? Yes, by the second rule. Do you guys see that? So multiplying the first row by 1/2. Oh, by the way, the way to get to that, to achieve that objective is not unique. So actually, let me give you two different ideas. So one way would be, well, I can either multiply the first row by 1/2, and I would get the desired entry, the front entry, the leading entry as we would call it, the leading entry of that row equal to 1, and then I need to still calculate the remaining entries, which will end up being 3/2 and 1/2, and this one will be 0. Alternatively, I could have, using that third property, I could have multiplied the second row by -1 and added to the first row. Actually, I think that one turns out to be probably easier. So let me just go ahead and do that. So I'm multiplying the second row by -1 and adding it onto the first row. So -1, so +1 times -1 is -1, plus 2 is a 1. -1 times -1 is a 1. 1 plus 3 is a 4. Do you guys see that? And then 0 times -1, so that one won't affect anything. And finally, 1 times -1, that's -1, and add it to the first row. The second row will be untouched. Do you guys see that? 1, 0, and 1 here. All right, so once you have a hold of, so have a feeling for what's going on, let me just go ahead and move this a little bit down. So that's our ultimate objective now. I want to have it on the screen so I don't lose touch of what I was trying to achieve. All right, so we have some more work to do, right? Next, I'm going to add the first row. So sorry. I will multiply the first row by -1 and add it to the second row. So the first row will remain as it is, 1 minus 1. And the second row suddenly will become 0. So I'm multiplying the first row by -1 and adding it to the second row. 4 times -1 is -4. -1 is that one will be a -5. And 1 times -1 is just -1. Adding it to 0. Oops, sorry for that. Adding it to 0 is just -1. And finally, -1 times -1 is 1. Adding it to 1, that will give us a 2. There you go. Next is that now we're almost there, right? So far, I have achieved the following. Let me just highlight them. I got that 1. I got that 0. So next order of business is to take care of that 1 over here. To make that 1, I need to probably multiply the second row by -1/5. All right, so let's just do that. So multiplying the second row, so the first row is intact. I have not done anything to the first row, but the second row is to be multiplied by -1/5. So that 0 times -1/5 is 0. -5 times -1/5 is a 1, which is perfect. -1 times -1/5 is 1/5. And 2 times -1/5 is 2 over 5. And there you go. So now in the next step, so we're almost done. The only thing missing is that 0. I need to turn this into a 0, but that's easy now. I'm just going to multiply the second row by 4, actually by -4, and add it to the first row. So let's just go ahead and do that. So 1, because 0 times -4 is just still 0, and adding it to 1 doesn't change anything. 1 times -4 is -4, adding it to 4 is 0. 1 over 5 times -4 is -4 over 5, adding it to 1 is 1 over 5, and -2 over 5 times -4 is 8 over 5, adding it to -1 is 3/5. Alright, now the second row will not change. And guess what? We have the answer that we needed, right? So as you guys can clearly see, on the left hand side we have the identity matrix, that 2 by 2 identity matrix with the diagonal consisting of all ones and off diagonal entries, all zeros. And so what came out of this turns out to be the inverse. So this is the inverse of this 2, 3, 1, -1 matrix, right? So inverse of actually, let's just use the notation, right? So in a sense, we decided to call that guy as 2, 3, 1, -1. So when I took the inverse of this, it turns out that this thing came out as 1 over 5, 3 over 5, 1/5, and -2 over 5. Now, matrices have this additional property where we can multiply. If we multiply a matrix by a number, that multiplication would go inside and it would multiply each entry, or vice versa. In this case, what I'm thinking is, because there's a 1/5 in each of the entries inside this matrix, I can move that 1/5 out. And so what's left inside is just a 1 here, a 3, a 1, and then a -2. There you go. So now that we have our inverse matrix, we can go back to the original wording of the problem. So remember that our goal was to solve this, let's remember the very first question. The question was to solve this system of equations. Maybe I should have written it here, solve. So we're trying to solve this system of equations, which we already did manually, but we want to find a more systematic way to solve this, because this is an easy question. 2 by 2, of course you can do it manually. What if the question is a 10 by 10, 10 equations and 10 unknowns? Suddenly you will be stuck. You don't know where to start from. So matrix algebra, linear algebra, helps us organizing our operations, right? So and does the eliminations in a straightforward manner. All right, so we turned that system of equations into this matrix form, after which we realized that all we need to find x and y, the values of x and y here, is to isolate x and y on one side of the equation. So basically, in a sense, dividing both sides by this matrix, or rather we would call it by multiplying it with its inverse on both sides of the equation. If you multiply both sides of the equation with the inverse of this, okay, let's just not do it. For those of you who didn't enjoy this notation here, let's just totally skip it. So I'm just going to multiply both sides of the equation by this. Let's just do it. 1 over 5, 1, 3, 1, -2. And I have the original 1, 2, 3, 1, -1. And on the right, and we still have the xy vector. And on the right hand side, we do the same thing. Oops, I forgot the 1/5. On the right hand side, we also multiply the 29, 2 vector by that same thing here. And we keep that 29, 2. There you go. Well, from what we did, because this is effectively the inverse of this, these two, when you were to multiply them, it will give you the identity matrix. And let me just go ahead and prove that. So let's keep that 1/5. Now let's go ahead and multiply that 2 by 2 vector by that 2 by 2 vector. And just for the record, whenever you multiply two vectors, like in this case 2 by 2 by 2 by 2. So what happens is that the new matrix, the resultant matrix, will be such that, first of all, two matrices can only be multiplied if the number of columns in the first matrix is equal to number of rows in the second matrix, which it is in our case. Then the dimensions of the new matrix will simply be these two numbers, 2 by 2. There you go. So I'm expecting a 2 by 2 matrix right here. Well, the 1/5 is out. So 1 times 2, that's a 2, plus 3 times minus 1, that's a minus 3. So 2 minus 3 is just a minus 1. All right, so maybe I should have written it like this. Let me... Yes. Okay. So 1 times 2 is, oh, sorry. Oh my gosh. All right, so I already messed up. Sorry for that. Let me just back up a little bit. I was supposed to, let me just do the coloring again. I was supposed to multiply this row with this column. Sorry for that, component-wise. So let's just do it one more time. So 1 times 2 is 2. 3 times 1 is 3. 2 plus 3 is 5. There you go. Let's do it again. Next is to multiply this with the second column. So 1 times 3 is 3. 3 times minus 1 is minus 3. 3 plus minus 3 is just a 0. Perfect. So next is this row, second row in the first matrix with the first column. So 1 times 2 is a 2. Minus 2 times 1 is a minus 2. Adding those two, 2 plus minus 2 is just a 0. And finally, the first row, the second row in the first matrix, and with the second column in the second matrix, 1 times 3 is 3, minus 2 plus minus 1 times minus 1 is 2, 3 plus 2 is a 5. And that's it. And we still have the x times y over here. Well, on the right hand side, we can keep doing the same thing. So we'll just go ahead and multiply that 2 by 1 matrix with that 1 by 2 matrix. Oh, sorry, 2 by 1. Sorry for that. This one was 2 by 2. Sorry for that. And the second one is 2 rows and 1 column, so 2 by 1. So what we realize that the number of columns in the first matrix has the same number of rows in the second matrix, which turns out to be a vector. A vector is a matrix with n rows and a single column, right? So because the twos match, so the resultant matrix will be 2 by 1, 2 rows and 1 column. So basically it will be just two numbers like here. All right, let's just do it. So 1 times 29 is 29. 3 times 2 is a 6. 29 plus 6 is a 35. And 1 times 29 is a 29. Minus 2 times 2 is a minus 4. 29 minus 4 is a 25. Now, let's go back to the left-hand side. Now, remember earlier that we mentioned whenever you multiply a matrix by a number, that number is to be multiplied with all the entries inside the matrix. And that's what we do. 5 times 1 over 5 is 1. 0 times 1 over 5 is 0. 0 times 1 over 5 is 0. 5 times 1 over 5 is just a 1. We call this special matrix the identity matrix. And it has a very special purpose. The identity matrix, when you do matrix multiplication, turns out to be the identity element, really, with respect to the matrix multiplication. So therefore, anytime you multiply a vector, like in this case xy, by this identity matrix, you get back the xy vector. All right, so on the right-hand side, we'll do the same thing. That 1/5 will be multiplied with both of these. So 1/5 times 35 is just a 7. 1/5 times 25 is just a 5. Now let's keep going on. So on the left-hand side now we have, okay, let's just, for the fun of it, I know the result should be xy, but let's just prove it. So this is a 2 by 2 matrix. This one is a 2 by 1. The twos match, the middle terms match. So therefore the resultant matrix should be a 2 by 1 matrix. So therefore it will look like this, two numbers over here. On the right-hand side, we already have found 7, 5, a 2 by 1. That's perfect. Okay, let's do it. So 1 times x is x. 0 times y is 0. X plus 0 is just x. 0 times x is 0. 1 times y is y. 0 plus y is just a y. And that's it. So on the left-hand side, we have a vector, a 2 by 1 matrix, if you want to call it that way. with entries x, y. On the right hand side, we also have a 2 by 1 matrix vector with entries 7 and 5. So that implies that x must be 7 and y must be equal to 5. That's it. We solved the same question using linear algebra. So if we go all the way up, you will see that we got the same answers earlier, right? So this one and this one, we got the same answers. All right. So there's a couple of alternative ways to do all these calculations. But before I do that, let me first go ahead and stop the recording here. In the next video, we will talk about how to do these calculations using Microsoft Excel.